Great. So I would like to introduce James Caverlee. He's a professor and Lynn 84 and Bill Crane 83 faculty fellow at Texas A&M in the Department of Computer Science and Engineering. He received a BA in economics, of all things, from Duke, then went on to do a master's in economic engineering, as I understand it, and computer science at Stanford, and then a PhD in CS at Georgia Tech. He's done a lot of research on recommendation systems, social media, information retrieval, et cetera. So really within the area of, let's say, computer-human interactions. He's an associate editor at a number of places, a number of important journals, including IEEE Transactions on Knowledge and Data Engineering. He's also co-chair at at Wisdom, and senior program committee member at a couple other major CS conferences such as KDD. And with that, I would like to let you take the lead.
James. Thank you for the very kind introduction. And let me share my screen here. Yeah, and just sort of as a point of order, I do have my chat window open, and so I'm used to my class. I have the chat window open. I feel like our education is becoming more and more like Twitch, so I do my best to kind of watch the chat. So if you have questions and whatnot, yeah, fire it in the chat, and I'll try to hit it. Yeah. Anyway, so thanks so much for the introduction and for inviting me here to speak. It's a real honor, real pleasure. And I hope we have a fun-ish time sort of in this remote Zooming world we live in. So I'll do my best to kind of hopefully keep this party moving. A couple of things, some special thanks. Obviously, Keith, thank you so much for inviting me. Mara, thank you for coordinating all this one-on-ones and coordinating the talk. Everyone who's joined us just now, I really appreciate that. This is work that I'll primarily be talking about that was led by my student Zoe. And this has been work funded by NSF. And I should also mention, I guess, part of our more recent funding also has an Amazon component to it as well. So I should acknowledge all of that. And one more kind of before I get into the talk, one more announcement. This is actually really important. I'm on the search committee. I'm on 2 search committees at A&M, and we are hiring. So this is, if you've got great students, postdocs, I'm not trying to poach anybody, but we are hiring, assistant, associate, full professors in a variety of areas. You can see them all listed there, including multidisciplinary. So this is one search. We have multiple positions. We also have a special data science search. So one of those faculty appointments would live in CS and one would live in industrial engineering. So again, if you have any great people, ping me, and you can find me online, or you can email me at caverlee@tamu.edu. And we also have a bunch of, we call them academic professional track positions. We're trying to move away from kind of like the traditional kind of one-year lecturer position. So these usually have multi-year appointments. It's primarily teaching, but it also has either a service or a research component. And we've tried to design them so you have sort of multi-year contracts, and we're trying to design them for long-term professional development. So just as a quick plug, if you know people, please let me know. Okay. Now on to the talk. Yeah, so the main topic is recommender systems. And this is an AI seminar. And so I was thinking about, to me, AI is obviously a very broad topic. Recommender systems to me are really kind of a fascinating kind of application space that have kind of a lot of neat opportunities for AI for new algorithm development. And so to me, they're kind of a great test bed for us to try out some of our ideas. But I think we're all familiar primarily with the main idea. We've all used Netflix, but the idea is usually we have lots of users, we have lots of stuff. We usually call those items. And in the middle, there's some kind of mechanism, some kind of algorithm. And we're trying to figure out, what is the right item to give, not to everybody, but to personalize it, right? To give to different users on the other end. And we also have a number of stakeholders here, right? So you have users, you have item providers, you also have the platform itself. And so when you start thinking about fairness or bias, we have kind of a lot of stakeholders, and we have to think about like, how do we model their interactions and their expectations and so forth. But yeah, so recommender systems themselves are, ubiquitous. So obviously Amazon for buying stuff. If you think about our information diet, and so if you think about how Facebook decides, what items show up in your news feed, that's fundamentally a recommendation problem. You have thousands and thousands of potential items. Which ones of those get put into your stream? Also, you're seeing a lot of a kind of movement more recently in personalized health, as well as more traditional areas like movies and music and so forth. So to me, it's kind of a rich space, lots of different kind of opportunities here. But of course, like any kind of AI or ML system, there's bias, okay? And there's lots of different kinds of bias, right? You have just an inequality in who's participating in these systems, right? So necessarily by language, right? So if it's a sort of English dominated versus another language. Another main issue is popularity bias. Sort of popular things accumulate more views, clicks, hence they remain popular and can squeeze out fringe items. And I'm not going to go through all of these, but the point is there are kind of lots and lots and lots of biases and kind of odd kind of phenomenon that can arise. And so what we've seen really in the last few years, this is an area I'm really interested in. But if you have interest in bias and fairness issues and recommendation, there's actually a really nice tutorial this summer. So anyway, I recommend you take a look at that tutorial. But if you're interested in this area sort of more broadly beyond what I talk about, there are lots of papers in all these top conferences. We've had lots of dedicated workshops, tutorials, special issues. So there are a lot of people working in and around this space. So you'll see, I'll talk about a couple of types of bias and fairness issues, but it's really kind of a wide space with lots of really interesting work. And so I kind of want to point you in that direction and make sure you stay on top of that. Okay, now, a little kind of prelude into how I got into this sort of fairness and bias topic. So kind of a few years ago, I was really, really into expert recommendation, okay? And so this was, it's a recommendation task. And so instead of recommending movies or, music or whatnot, or products, I was thinking about, gosh, we have, in this case, I was looking at social media, and we have lots and lots of, sort of regular users, but kind of hidden amongst them. The idea was we have, using the wrong thing here, hidden amongst them, right? We have kind of these experts. And so I put these, sort of these big ideas, these stars popping off of them. And so the idea was, gosh, wouldn't it be great if we could go find those experts and use them sort of, for, this expert here, might get recommended to this person, right? And so the idea here was you might find interesting people to follow. You might find people who could answer your question. There's sort of a lot of sort of downstream applications that we were excited by in doing this kind of expert recommendation, okay? And so we had a bunch of papers and we were looking at this problem, and a lot of it was in the context of social media, and so in particular in terms of Twitter. And so what we had done at the time was we're trying to figure out who's an expert. And so there's this artifact called a Twitter list. And so basically we said, aha, so a Twitter list is a way that I can basically put you, like anyone I follow, on a list, and I can label you, okay? And that way I can kind of curate or cultivate who I follow. And so for example, we might have this list creator has placed these two people on a list called sport, okay? And so when you aggregate that, you have lots of list creators and lots of lists and lots of these labels, we would say, aha, so these users are cultivating these experts according to different topics, okay? And so that's kind of like the basic setup of a lot of the research we were looking at, okay? And so what we did is we said, okay, so we're going to basically apply some sort of traditional recommendation methods. And so if you're familiar with this, there's like matrix, or you can think about it as a tensor factorization. And so in this case, right, we have our users, right? We have our experts. These are other users, but we sort of consider them special users. We call them our experts. And we can align them according to different topics. So here I have business and sports and on and on and on. And so the idea was, okay, we can basically, try to fill in, we want to fill in these missing entries in the matrix to recommend to a user, oh, here, we know some of the people you have liked. Here are some people you might want to like, or you might want to interact with, okay? So now we have basically sort of a standard kind of recommendation task where we can now recommend experts to users based on these interactions that we've collected in the past. Okay, so we went and did that, and it was exciting. But what do we notice, however, in practice? And in this example, and I think in several of these examples, I'm gonna binarize on gender, but our model extends to 3, 4 multi-way how we split the data. But in this case, just sort of for simplicity of presentation, what we observe, right, is that if we looked at the historic interaction record, is we would see like these big imbalances. And so, for example, like in this business category, you might see lots and lots of historical feedback, like lots of likes or putting people on lists that were to male experts, sort of dominating women, right? And maybe it was not as imbalanced for some other topics, but you saw this kind of big distortions, right? This is sort of a natural, not say natural is the wrong word, but this is not unexpected if you've looked at any kind of these big data sets, right? There's oftentimes these sort of big imbalances, okay? And so the idea is sort of encoding some historic bias into the data set. So then what happens is we build our model based on this historically skewed data set. And then what we discovered, right, is that we were generating even more skewed recommendations. So just by applying a traditional recommendation method, right, we would take that 4 versus 9, and then it would end up augmenting it and pushing it even higher, right? And sort of squeezing, in this case, squeezing out women experts for business, okay? And for many of you, this is like a duh moment. Of course, we know there's algorithmic bias, and this is a very kind of obvious finding. I'm a little slower, and to me, it's like I had to see it in front of me to recognize, like, wow, this is a big problem. And this is really when the light went off for me, okay? And so we started looking at this problem. We said, gosh, how can we fix this, or how can we at least give policymakers or give platforms tools and knobs to tune so they could maybe pick different ways that they want to deal with this kind of imbalance. And so at the time, we hooked on to this idea of statistical parity, which is a pretty common idea in this fairness literature. And the main idea was we're going to basically try to force that we have a similar probability distribution for our groups. So in this case, I'm showing you a sort of 2 groups, but again, it could be extended to 3, 4, or 5 groups. And so the idea with statistical parity is we're trying to go from this unfair example where we have this imbalance, and we're trying to force it, in this case, to be equal. Okay, so we have if we've equalized it, right? The idea is then we can say we sort of diminish that kind of bias in the historic feedback, okay? So this is the idea we had at the time. It's kind of a pretty common metric. And so we took that and we plugged it into, I was showing we were doing like a matrix factorization type method. So it turns out we were doing a tensor-based factorization method. And so we ended up cooking up this method. And I'm not going to walk you through the details of how it worked, but I just want to give you a sense of kind of what we were thinking about as we attacked this problem. And essentially the idea was we were going to take those biased historical feedbacks. And when we did some factorization, we were going to try to isolate the sensitive features, like corresponding in this case to gender. And then we're going to try to squeeze that out so that we could go recover, in this case, a balanced or fairness-aware recommendation, okay? As another thing, in terms of when you name things, our original idea was fairness-aware recommendation with tensors. We switched that around, and I'll leave it as homework to figure out why we switched around the name like we did. You got to be careful when you name these things. Okay. So anyway, this was for us, it was kind of like our first foray into this topic. It was combining fairness and recommendation. We published this, I guess, in 2018. But if you're sort of watching kind of closely, if you're sort of very connected to fairness and/or recommenders, you may see some problems here. And so what I'm going to try to do here is kind of launch into sort of the rest of the talk as to kind of the strides we've made in our group of trying to deal with some of those challenges. So the good news is, like, we proposed this model and it seemed to work pretty well. Okay, and the idea was we were getting fairness depending on how we measured it. Well, we were balanced that with recommendation quality itself. So that was pretty exciting. Okay, yeah. However, like if you take a very careful look, what we were doing is we were actually, and a lot of the literature at the time was trying to consider bias from the perspective of the predicted score, right? So for example, like, we're going to put a number, okay? And we're going to try to then sort of balance the scores between, in this case, men and women, okay? But of course, when we interact with recommenders, we don't care necessarily about the score. We just care about, in many cases, what are the top K? What is the ranking list of items? So one of the first kind of issues we had with our own work and with other works was that we were just looking at an intermediate step, right? We were focused on the scores, but just because the scores might have been balanced, didn't mean that we would have an unbiased recommendation, right? Because we weren't looking at the rank order of things, okay? So the first big idea is we need to consider the rank of items when we either assess or try to mitigate any kind of bias. The second issue you'll notice is that we had a very, particularly in this case, we thought a sort of strict fairness definition, statistical parity. And what I'm going to try to do in the next few minutes is try to argue why that might be too strict in many, many cases. And we might want to consider other ways to assess fairness to drive our methods. And kind of the third point, in fact, I gave a talk on this paper at one point, and a lot of people in industry were saying, wait a minute, you know, like you're assuming a particular, like in this case, a tensor-based recommender model. And you know, say in production, we have lots of different kinds of models. And so you're asking me to go in and basically like, you know, tear up my production model to try to bring in some fairness. And so that's another issue we had, which is basically, you know, we designed this method for a particular kind of recommender model. And so sort of this last big issue we've been thinking about is, can we kind of decouple our method from a particular algorithm? And so then we can potentially apply it to lots of different algorithms and not, you know, not sort of require you have to be using this particular kind of core recommendation method. Okay, so hopefully this is like the big motivation and kind of what I'm going to talk about for the rest of the talk is kind of how we overcome these. And I'm going to talk about kind of two recent works we published, and let's get into it, okay? Oh, and by the way, I'm still looking in the chat. I've got a couple of messages there, I guess on the private side, but if you have any sort of questions that you want me to share publicly, I'm happy to take them there, okay? All right. So, okay, so the first thing I want to get into is a paper we just published this year, and it's looking at what we call under recommendation bias, okay? And you'll see hopefully how we deal with some of these questions that we raised in our original work. So hopefully this picture should look quite familiar to you, sort of a stand-in for something similar to what I just showed you, okay? And so in this case, I'm looking at something different. It's not experts, but imagine we have different kinds of items. In this case, you have jobs. And so we're trying to recommend these jobs. So these are, you know, these are our items, like always. These are our users, like always. And you can imagine, again, we might have some imbalance in the feedback, right? And this is, again, the sort of standard thing. In this case, this example is, you know, high-paying jobs get lots of feedback, lots of interactions, whereas maybe these nonprofit jobs are not getting lots of feedback. And so then you go shove that into any sort of standard recommendation algorithm that is not bias aware. And then on the output side, what we're going to see is, notice now I'm not looking at just the scores we assign, but I'm considering the actual rank order of the items, in this case, jobs, and how they're being shown to the different users. And so in this case, if we look at just the top two items, so now we have a rank order. If we just look at the top two items, you know, we'll notice that like the sort of the blue high-paying jobs are dominating the red nonprofit jobs, okay? And so the idea of what's happening here is, again, the algorithm is basically taking it, you know, sort of taking advantage of the imbalanced distribution of the feedback for items. The algorithm itself has no awareness of the bias. And so as a result, we're seeing this under recommendation is how we call it. So some groups, in this case, non-profit jobs, were being under recommended comparing to other popular item groups, okay? And so again, you can swap out, it doesn't have to be jobs, it could be, again, these experts, it could be any other kind of item group where you have this imbalance distribution in terms of their historic feedback, okay? So this is the first idea. We have sort of these item groups are fundamentally going to be underrepresented, okay? So we need to somehow measure that, right? And so if we can measure that, then maybe we can try to mitigate or deal with that kind of imbalance, this kind of under recommendation bias. And so I already introduced this concept of statistical parity, right? And so I've tried to assert, and hopefully you bought it, that just because I do a good job on predicting scores, it doesn't necessarily correspond to the rankings, right? And so a very natural step is to then say, well, we're not going to consider statistical parity for the entire group. Excuse me, on the score perspective, we can consider it for all the groups on the top K, right? So that just leads to a very natural definition of what we call ranking-based statistical parity. So now what we'll do is we'll measure not across the entire, but in this case, the score, we'll now look at in terms of the top K, with respect to all of the groups. And so the hope here is we're trying to maintain parity at that top K level, right? So to overcome that under recommendation bias. And so again, going back to sort of this sort of a simple example, in this case, right, you know, the probability being recommended in this case, now that we're looking at the actual top K, might be imbalanced. In this case, might be unfair for, in this case, women. And so how can we try to overcome that? Okay, so so one of the things I want you to notice here is that when we look at statistical parity, it's, you know, basically really important when we have item groups that have sensitive attributes. And so, you know, we have a lot of protected attributes when it comes, in this case, you know, for jobs, it could be gender or race, or you can imagine some other protected attributes. And so in those cases, it's very natural to try to encode that into how we assess this kind of bias, right? But there are many cases where we don't necessarily have sensitive attributes, but there still may be fairness issues, okay? And that leads us to a second metric that we're going to talk about, which is a variation of equal opportunity. This is what we call ranking-based equal opportunity. So equal opportunity is, again, it's a pretty common approach you'll see in the machine learning literature. But now we're looking at it in terms of a rank-based approach, just like our rank-based statistical parity. And so the point here is that you have many scenarios, right, where, you know, we may not have those sensitive groups, but we do want recommendations to be driven by user preference. So the idea is that user may have the same chance of seeing items from different groups, you know, subject to that this user likes them, okay? And so the idea here is we're trying to get the same true positive rate. This is corresponding to equal opportunity, the same true positive rate across the item groups. And here's just sort of a silly example, but here is this user, and this is in the context of, you know, let's say movies. And it could be, again, part of this is, you think about this as like, if we knew the user liked, I guess in this case, horror and sci-fi, right? So those are sort of the actual user preferences. But if the recommendation model only recommends sci-fi, we've missed out on this opportunity to recommend this other kind of item that belongs to a different group, okay? And so in that case, the user's preferences are not captured. And so we're making a mistake. And so this leads to what we call ranking-based equal opportunity, okay? And again, so basically it's a slight variation of our statistical parity definition, whereas now we're capturing not just the over the top K, but we also consider whether the user liked the item from that group, okay? Cool. So now we have our kind of our two ways to measure this. We have this RSP, statistical parity, and we have our REO, our rank-based equal opportunity. Oh, so, okay, and just for REO, just to give you again, so again, in this case, this particular user, right, was recommended horror and they liked it, and they liked sci-fi and liked it, and there's a big imbalance here, right? And so the idea here, it could be that this under-recommended item group might then receive fewer and fewer feedbacks over time. Okay. So let's look at it in practice, okay? So we have these kind of two ways to measure this under-recommendation bias, right? And so what I'm showing you here is, this is from, another sort of caveat to a lot of this research, which is in that original work when I was talking about Twitter experts, you know, we actually had real data on users and experts, and we had real data in terms of gender and race and things like that. What you'll find is there are not a lot of great data sets for studying fairness or bias in recommendation. And so what a lot of people have done, what we've done, is you adopt kind of these data sets that have groups to them. So in this case, the standard movie lens data set. The challenge here is the groups are like by genre, right? And we've done some similar work where you can look at like Amazon or Yelp reviews where you have, the type of restaurant. And so the issue is they have different kinds of groups, but they tend not to have sensitive attributes. And so I'm just putting putting a pin in this point here. This is something as a community, we've not done a really good job of developing really nice data sets that have these protected attributes for doing this kind of research. So just so you know, it's like, wow, it's kind of weird you're studying movie lens. It's like, we're doing the best we can to find data sets that do have groups where we can then study this. But what we'd really like to do is look at data sets that have a lot of these protected attributes. Okay. So what I did here is we took a standard recommendation method, and you can try lots of different ones. In this case, I'm using something called BPR. which is again, just sort of it's a fairly standard, pretty popular recommendation method for data sets that have implicit feedback, like clicks and whatnot. And so what I'm showing you on the left-hand side is just the number of feedbacks per item for different item groups. And what you can see is like, there are some popular, in this case, groups, sci-fi, and there's some not popular ones, horror, and you have this sort of downward slope. Well, if you go measure the statistical parity or the equal opportunity, so again, we're looking at the probability given the group, the probability given the group and the user liked it, you see this preservation of this imbalance, right? You see these downward sloping curves, or these the bars are downward sloping following the original distribution. And so our argument here is that, yeah, and if you can plug in some other methods and you'll see something quite similar, which is basically, right, these existing recommendation algorithms are generating this kind of bias, right? So they're overserving some groups and they're underserving some other groups. Kind of not surprising, okay? So what we're trying to do is we want to have methods that can help us overcome that imbalance, right? That, again, we're not claiming we have the right way you want to tune the knobs, but we're trying to give you, the platform, or you, the policymaker, knobs to tune so you can potentially debias. And so we end up hopefully with sort of a flatter distribution, okay? And so we have this thing called DPR, which is basically just a debiased personalized ranking. And so the main idea here is we're going to try to decouple the predicted score with that group attribute. And so in here, it could be genre, but you can imagine it could be gender or race or whatnot. And then we have another sort of little trick you have to do is because we're dealing in terms of rank orders, and we have to then normalize all the score distributions to align predicted scores with ranking positions. So we can overcome that problem I was arguing for earlier. Okay, so let me show you some of the details on how this works, and then I'll show you some of the results and if it works. Okay, fingers crossed. So what we're going to do here, and I'll walk you through it just for statistical parity version, but there's also a similar construction for the equal opportunity one. So we adopt a pretty standard kind of adversarial learning framework. Excuse me. And so what I want you to notice here is we have our BPR. So this is basically, we're using BPR, but the idea is this could be any recommendation algorithm. And so the idea here is if you compare it to that earlier work I showed you where we were tightly coupled with a matrix or a tensor factorization method, like we worked in how we did the factorization. Here we're basically saying is, no, you can plug in whatever module you want here, and that's fine. So this is sort of meeting one of those challenges that we were facing, which is how do we decouple this debiasing from the particular method? And so what is it taking as input, right? It has the user, and then it has two items. And so if you know how BPR works, it's going to compare sort of the preference score for those two items for a particular user. And so what it's going to generate then are these two scores, okay? Let's see, oh, sorry, I'm on the wrong thing here. Yep. So, okay, so we're going to take in those users and item pairs. We're going to generate those scores for the two, okay? And what the discriminator is going to do is it's going to take those scores and it's trying to figure out which group you belong to. So again, if this is gender, or in this experimental case, if it's genre, the idea is these are those groups that we care about, sensitive attribute defined groups or by genre or by whatever. And so what the discriminator is trying to do is, right, to take those predicted scores out of the recommender and then try to guess which group you came from, right? And so what we're trying to do is, we would like to be able to then generate recommendation scores such that the discriminator can't tell which group they came from, okay? And that's the main idea. We're trying to minimize this loss, this adversarial loss for these two group guesses that we've made essentially, okay?
James, if I may briefly cut in, I was just wondering, so you're only using the score to infer the group? Yeah, in sort of the basic setup, yeah. But maybe I'm going to lead your question, which is, could you augment it with other things? Absolutely, yeah. Mm-hmm. So in short, I guess what this is basically doing is it's forcing all the distributions, the score distributions across groups to be equivalent, right?
So in the extreme case, right? So you have That's right. So like you could imagine if it was totally flat, we would have no bias, right? But we would also probably not have very good recommendation utility. And so that's the idea is sort of this, there's this minimax gain between those two kind of competing interests. That's right. And so it turns out there's a parameter you're going to throw in here, which is trying to balance sort of which side, so sort of a tunable parameter we do have, which tries to balance those two. So it's exactly your point, right? Which is we're making this min-max game where, right, we're going to have, we have the BPR component, right? And then we have this adversarial component. We're trying to minimize this BPR loss, right? So we have the conventional BPR loss. Again, don't worry about the details of this if you're not familiar with BPR. This is all fairly standard. And then we have this alpha on top of this adversarial component, right? That's trying to predict the group that corresponds to the different for the different items. And then this is where you kind of get into the weeds, and I really don't want to spend a lot of time on this, but you'll notice there's also this kind of another component here on the right, which is this trick we have to do because the user score distributions are not normalized. So we try to normalize them. And we have sort of a trick we have to do to try to get the scores to correspond more with ranking here. I'm not going to walk into the details of that, but we're basically trying to force them to the sort of a normal score distribution for our users. Okay, so that's the setup for this thing. And so let's go, we're going to throw it at our data, and I'll show you one of the results. And so what I'm trying to show you here is, this is that original, this is that original sort of downward sloping distribution, right, of in terms of statistical parity, in terms of our different genres. And the idea here is, right, we're hoping to see sort of it's flatter, right? We're trying to sort of equalize these. And similarly for the rank-based equal opportunity, similarly, we're trying to go from sort of this downward slope to sort of some flatter distribution, right? And in particular, if you think about equal opportunity, if you just focus on this right-hand side, right, it's the idea is like, it turns out, the user actually likes these things and will click on them. And so you don't want them to be here, right? Where in this case, horror is so low, right? The user actually is going to like them. So we want to promote them. This is a good thing. And we have to make sure, we do a good job of that. So this is just sort of an illustration. But then we go and run some experiments. And this is on, again, several of these different variations of this, sorry, this is all on Movie Lens, but we have some other ones in the paper. And so what I'm showing you here is, this is an F1 score. This is sort of, think about this sort of as a recommendation utility figure. And these other two are measuring this RSP and this REO. So this is kind of the fairness idea. And typically, in a lot of this work, there's some kind of trade-off between the two. And so we're plotting here is we have BPR. That's just a fairness unaware, just sort of traditional method. We have our DPR. That's what we proposed. And then we have a couple of baselines that we had to adapt to this scenario. This one is the one I talked about earlier, and this is a regularization based. It tries sort of force these distributions alike through a regularization term. And so what you're going to notice, so sort of in terms of the recommendation utility, is we do eat something, we do pay something, right? So if you look at the kind of red-orange bar, it's down from BPR, right? Because BPR is unfair, but optimizing purely on this recommendation utility. But the good news is our recommendation utility is higher than for these other fairness-aware methods. And then if you go to the right-hand side, those two fairness figures, what we're noticing here, right, is again, those orange bars are super low in terms of the rank-based statistical parity measure and this rank-based equal opportunity measure, in particular compared to BPR, and is doing a better job. I guess here it's a little close, but doing a reasonable job compared to these other kind of fairness-aware methods. So those is kind of very exciting, right? So we're able to preserve this recommendation quality while bringing in some of this fairness. And again, sort of decoupled from the particular definition. I'm showing it here for BPR, but you can swap in another method and it works just fine. Okay, so takeaways from this piece, right? We have these two rank-based, very natural extensions of traditional bias metrics to this scenario. We have this adversarial learning model which has a sort of nice way we can balance the utility with fairness, and you can apply it to other algorithms. And, look, we ran a bunch of experiments. We showed BPR as an example has lots of bias, and we showed a way we can overcome that. Okay, so for us, it's very kind of exciting, kind of a neat result. Now, there's still some issues. It's like there always is, right? With research, there's always issues. We're always climbing the hill. We're always trying to do better. So one of the things we notice, okay, sorry, this is leading up to this next piece, which is going to show up at Wisdom. I guess Wisdom 2021 is going to be online. For those of you who went to Wisdom 2020, that was in Houston. For me, that was my last conference in person. I think for many of you, if you were there, it was maybe your last conference. So, I mean, we just got it in. This was in February of 20. We just got it in before everything went crazy. So anyway, looking forward to hopefully seeing people in person at a conference at some point and not just online. Would be very nice. But yeah, so this is essentially an extension of the work I just showed you. And so what I'm going to try to argue to you here is that we were talking about kind of group level unfairness, right? This is the case, it's genres, but again, it could be race or gender or whatnot. And I said, look, you can take a traditional method and it's going to generate this unfairness, okay? But I mean, fundamentally what you notice, right, it's something about the skewed popularity distribution is the thing pushing this, right? It's the fact that I'm showing on the left-hand side is the number of feedbacks per item. It's just life. There are things, there are items that receive more feedback, that get more clicks, okay? And so there is this skewed popularity distribution, which is fundamentally the mechanism driving the unfairness that we see. And so the main idea then is to say, wait a minute, there is this skewed distribution at the group level, but it also occurs at the individual item level, not just by group, okay? And so what we're doing in this work is trying to move from group level fairness to item-based fairness. And so our argument is basically, if we really want to study fairness in recommendation, we need to directly study the impact of item popularity on those recommendation results from the kind of the individual view, not this sort of aggregated group view. And again, what you'll see in a lot of the research in this space is there is a lot of work where you're worried about groups. What we're trying to do in this case is shift the focus now into individuals. Okay. And so what I'm going to do here is I'm not going to show you kind of our solution. What I'm going to try to do here is just sort of motivate what the problem is and show you a result. Okay. And before I wrap up. And so if you're familiar with popularity bias, right? People have been studying this for many years in many different contexts. When we think about it in recommendation, right, is the idea is, there are popular items that are recommended, hence they get more exposure, hence they're clicked more, they cement their space as popular items, and it goes on and on and on and on. And so you can think about popularity bias is sort of consistent with this notion of statistical parity. And again, what I'm showing you here is a figure derived from a movie lens data set. And what I'm showing you on the y-axis is the probability of being ranked, let's say in the top 15. And this is item popularity. So in this case, this is the most popular item that we're looking at. It has lots of feedbacks, okay? And you can see that the item that is the most popular, has the highest chance of being recommended. And you see it's a pretty clear curve up, right? So the idea what we're just seeing from this data set, right, is more popular items do indeed have a greater chance of being recommended, okay? And so you might think, in one sense, you might think, and indeed there are lots of approaches that have thought about this, which is, what if we just unilaterally flattened the curve? And we just said, no, the correct answer is, popularity shouldn't matter, okay? And so we're gonna flatten this thing. And so it doesn't matter how popular you are, all items have the same probability of being ranked, in this case, in some top K, okay? And so that's basically the assumption of a lot of conventional work in popularity bias, is trying to ensure the same exposure for both popular and unpopular items, okay? However, we're going to argue that it's a little weird and maybe is not appropriate in all cases, okay? So let me show you an example. We have a user. In this case, we have a popular item and we have an unpopular item. Now, again, imagine the user likes the popular item, so they've hearted it, they clicked it, okay? But they may dislike the unpopular item. Notice there is no heart there. They didn't like it, okay? And so the idea is, if we rank the popular item higher than the unpopular item, that seems like a good idea, right? The user liked it. The user didn't like the unpopular thing. So ranking a popular item above the unpopular item is quite reasonable, we would argue, okay? However, in a lot of work in looking at popularity bias this is an overstatement here, but there is a lot of work which basically says, we could instead, push the popular item down the ranked list and try to give it a rank similar to the unpopular item to sort of, we don't want popularity to be such an important factor, so we're going to push the item down. But then fundamentally, we know the user, in this case, likes that item, but we're somehow punishing that item relative to the unpopular item. Okay, so this is sort of the basic idea of the argument, which is, in this case, sort of, so there's a question. Why push down popularity? It could indicate higher quality. This is a great question. So wait a minute. Popular items might be popular because they have lots of other attributes. They are indeed better items, right? And so, yeah, we absolutely agree with that. That's exactly right. And indeed, the way our model is designed, it's designed to respect that just being popular is not a bad thing. But the subtlety here is what we're looking at is we're actually going to measure this in terms of, and again, we're going to measure it in terms of the sort of true positive of like the user actually liked the thing. And so the way we're going to do that in terms of like a train test split is, in the test set, we don't know if the user likes it. So we can only build our model over the train, right? But over the train, what we're going to say is, given two items, regardless of their popularity, if you like both of them, we don't want to let popularity let one of them, in this case, like dominate the other. So I think I have another example I'm going to show you. Hopefully it can answer this question. In fact, so this is, excuse me. So this is what we're trying to argue, which is, in this case, you have a popular item and an unpopular item. And if we condition on the fact that the user likes both of them, so our argument is, we're going to argue that if you rank, they're both liked. We don't necessarily want to penalize popular. We want to make sure that unpopular and popular kind of can live together, so that we're not punishing, if that makes sense, right? So in this case, right, we might push unpopular up, we might push popular down, but conditioned on, hopefully they're both going to be ranked highly because the user is going to like them both. That's kind of the argument we're trying to make. So let me go back to a figure here, which is what I want you to notice here on the y-axis is, notice I've now added in this, this user preference signal. The user liked this thing, okay? So now what I'm showing you here is, again, just like before, we still have item popularity. This is a very popular item. But now what I'm showing is these are actually items that the user likes. And yet we still see this big imbalance distribution, right? And so our argument here is that these are items that the user likes. And so what's happening is we want to not punish those low, in this case, low popular items, because the user's going to like them. Okay, that's kind of the basic argument. Yeah, and so in essence, right, if we can then try to flatten this curve, our argument is, again, in the context of the user will like them, our argument is that flattening this curve in this context is reasonable. Okay, that's the big setup. And again, so what we're trying to argue here is a lot of traditional popularity bias work in this space is not considering this actual user preference, this piece. And so our hope is, by focusing on that piece, we can, in this case, help promote, in this case, some unpopular items. So let me go. So we propose this popularity compensation method is what we call it. And I'm just going to walk you through a quick result here, and then I'll wrap up the talk. So thanks everyone for sticking around. So here, again, what I'm measuring is we have our BPR. Again, you can swap in any other recommendation method. And then I have, these are a couple of some sort of trying to adapt some conventional popularity bias methods. And then we have this, we call this popularity compensation method. And then what we're measuring here, well, sorry, and this is, in DCG, this is again, some recommendation utility measure. And so we're showing here is compared to BPR, right? We do pay, right? We do go down. Both of these go down. But relative to some conventional methods that try to, sort of in this extreme case, flatten everything, regardless of user preference, right? That would be, all this stuff here, that we do a better job, okay? And then we have a way to measure this, this bias, and I'm not giving you all the details here on how we did this, but basically the idea is, well, I guess I can talk about it. We're basically looking at sort of the correlation between item popularity and the ranking position for matched users who will actually like the thing. And again, what you're seeing here is that in BPR, it's really high, and that we can push it down a pretty decent amount while maintaining some recommendation utility. And so our argument here is that we can basically, this is a way we can begin to mitigate bias while preserving this utility. And in particular, compared to conventional methods that attack popularity bias, it's kind of like it gives us like a good next step and a good movement forward. Cool. And again, by the way, in this work, there's a, I'm not going to talk about it, but there's a theoretical component where we try to show that this popularity opportunity bias is a fundamental property of any of these factorization-based methods. And we have a lot more experiments, but I'm not going to get into all that. I didn't even really talk about the method. So I just want to take takeaways from this piece is this popularity opportunity bias is what we call it, which is basically taking into consideration this matched user preferences. These are the users who actually like it, which is, we think is like a fundamentally different way to think about this problem compared to a lot of the work that's doing a conventional popularity bias. Again, if you go into the paper, you'll see some more empirical and wholly theoretical work, which I did not talk about at all, showing the prevalence of this kind of bias that's inherent to these factorization-based methods. And then we proposed, and I didn't talk about this as well, this post-processing approach, but hopefully some experiments gave you the sense that it might work. Okay, so you have to believe me on that one. Now, I'll wrap up because it's tough talking on Zoom and it's tough listening on Zoom. So I appreciate everyone who stuck around. What I do want to say is we have a bunch of other works that I'm not talking about at all. We have some work on exposure bias. That was a Rex's short paper this year, trying to kind of compensate for the fact that like when you click on an item, it's not just a function of it being recommended to you. It's the fact that you had to be exposed to it. And so trying to take into account that exposure bias. And we had another short paper at Triple Dub last year looking at something we called target distortion, a customer distortion problem, which is a different kind of bias. So I got lots and lots of stuff in this space I'm excited about. But kind of where are we headed next? And like, what do I think is exciting? At least in our group, this is what we're focusing on right now. The first thing is user side fairness. Okay, so basically everything I've talked about today is thinking on the item side. Items have groups, items have protected attributes, items have popularity. How can we measure that? How can we mitigate any bias that may show up? But you could also think about it from the user side, right? Like if you look at different kinds of users receiving those recommendations, there may be bias there, right? And so, again, it could be by gender, it could be by race, but now on the user side. So trying to understand, one, how to measure that, and try to recognize the relationship between that user side and the item side issues. And are there, is there like a strong connection between them? Another issue in terms of all this popularity is, we're still digging on like some of these underlying mechanisms, right? So obviously popularity is not the only reason for bias, right? So you could imagine, a popular item could be just like an unpopular item, very different from other popular items. So there could be some unfairness that could pop up for lots of, you consider other attributes of the items, right? The other thing is, popularity is sort of this crude sort of proxy for lots of things, right? So really what you want to do is like untangle, what popularity means and kind of get down to the core mechanisms. And the last one, and this is a really hard one. And so you'll notice a lot of almost all of the work I presented, right? We're using some offline data set. And this is a lot of this work, particularly out of universities. You'll see some industry giants will do online recommendation experiments, but typically it's kind of hidden away, right? They'll report a percentage improvement, but we can't really inspect it. We can't see it because it's all built on proprietary data. And so what we're trying to figure out is, data sets, frameworks, and kind of experimental harness so we can study in the online recommendation scenario, right? So it's not like a one-shot game, but that we actually have bias maybe propagating, building over time, trying to understand the impact on users, items in the system, and then how to build interventions or mitigating strategies in that online scenario. And this is really hard because, we don't want to cook up a goofy simulation that doesn't correspond to anything real. And so it's tough, right? And this is just a big one because I think this is where a lot of the excitement is, which is how do we understand, we can propose some way to mitigate some bias. And if we do it one time, does it last, right? Or do we need to keep re-injecting it, every so many interactions, every so many time steps? And how long does it last? And how long is it effective? And we just don't know. And so to me, that's kind of like an exciting direction that we're thinking about. Okay, folks. So actually, I don't have a thank you slide, but that's all I got. I just want to say thanks everyone for showing up and listening. Appreciate all your time. And I'll shut it down there. Thank you.
Thank you, James. This was an incredibly interesting talk. We have about 5 minutes left, so I think we have time for maybe 3 or so questions. With that in mind, are there any questions people have?
This is always the tough part.
Yeah. Well, I certainly have one, which is so going back to understanding the long-term effect of these biases and how they propagate. This is actually very similar to some work on the wisdom of crowds. And I feel like these are two fields that are somewhat surprisingly similar, but ask questions from different angles. Wisdom of crowds research relates to trying to find the true quality of an item. And in this case, we're sort of trying to find the quote unquote, the quality, if you will, quote unquote, is sort of personalized to each person. So in the wisdom of crowds research, some of the work that I've been doing that I will be discussing later, we've found that there are long-term effects to these biases. These biases in how crowds behave can consistently produce either instability in the ranking, that is, say some items are just consistently ranked, or many items are inconsistently ranked high. Like it could be that they are ranked high in one world and one scenario and low in another.
Yeah.
And as well as that, once they're ranked in this particular scenario, they stay up there. If they're poor quality, but they're ranked high, they stay in that high rank over time. So there's sort of a hysteresis. I think that would be a way to put it. So have you explored ways in which, say, are there ways in which you've tried to adopt, say, wisdom crowds to better understand recommendation systems, or do you believe that there's sort of a...
yeah, okay, that's a heck of a question. I mean, I know some of that literature. I've participated very on the fringes of that community over the years. But no, I haven't, I think I haven't thought about it, to be honest, at all about those connections, but I think it's kind of natural. I mean, I think there've been some similar questions in terms of popularity and trying to understand these dynamics, but not necessarily in the context, right, of this recommendation where I've been spending a lot of my brain power. So no, I don't have an answer for that. I know we're going to talk later on today. So maybe give me some time to think about it, but
Absolutely.
That's a really good point. Yeah. To connect those two, which I think is kind of a clever idea.
Yeah.
I got a question in the chat. Thank you. But how do you some? What about higher stakes recommendations? Yeah. So this is interesting, right? So the question is basically, right, there are some systems where, getting the, it could be the top one recommendation is all that matters. Versus, top, if you're thinking about music, top 5, top 10, who cares if you screw up a little bit, because it's not like a long-term impact. And then some of these decisions, right, naturally have kind of very long-term impacts, like for, the point in the question, which is, hiring someone. You don't want to unnecessarily, it's hard to undo those decisions. Yeah, so, I mean, again, what we're modeling here is we're not at all modeling the sort of the, I don't know what you call it, sort of the hardness or the degree of impact of these decisions. The models that we're all looking at are quite agnostic to it. I'm trying to think of, I mean, I've seen people do some work in terms of like dating recommendations, which is a little more high stakes. I mean, in that case, you're actually committing to potentially like spending time and seeing a person, which is quite different from clicking a link or whatnot. So I would just say, I don't have an answer. I've seen some isolated work that's looked at some of those scenarios, but I've not seen anything kind of comprehensive that compares them to kind of some of these other spaces. So you guys are giving me great ideas.
Jim, this is Emilio. First, I wanted
to
just pop by, show my face. I haven't seen you in a couple of years, so it's great to see you. The question that I have is, if I understood everything correctly, the most of the, if not all of the models that you basically developed assume that you, in the fairness space, assume that some of these fairness attributes are visible or accessible by your models. So you know that, for example, gender or race or whatever it is your sensitive attribute. You know that you want to ideally preserve that kind of maybe balance. Do not introduce the type of bias that you would observe in the real systems and so on. Have you thought about how to generalize this problem when your models do not have access to these sensitive attributes? I mean, in many cases, when we are thinking about even these high stakes recommendation systems, just to connect to the previous question, if you're thinking about recommending, whether to give a mortgage to someone or not, a loan, or whatever, right? These models don't have access to those type of information because there are regulations, laws in place. The same for discrimination laws in case of hiring, etc. But there are obviously features that are collinear as well, so that are correlated. Maybe you don't say your race, but there are features like that correlate with your race and that will introduce the fairness. So maybe the two parts question: how do you do it without access to attributes, and how do you address the issue that your model could learn predictive features that are correlated with hidden unfair features?
Yeah, so there was some recent work this year out of Google. I can send it to you offline, which is basically trying to do it in I think it's a classification context, is assuming you don't have the attributes, sensitive attributes. What we've tried to do is, in some of these cases we have them, but like in our work where we're looking at popularity, we're basically moving away from the sensitive attributes and we're trying to measure something that is visible, which is purely like, the number of feedback something has had, and look at it in that context. And I would say part of the practical issue is, for a lot of the data sets and a lot of the context we're looking at, we don't have the sensitive attributes. And so as a result, when we try to develop our methods, we're trying to identify biases that may not even require a sensitive attribute because we don't have those good data sets to measure it in. Hence, it's kind of hard for us to try to demonstrate something, at least in a recommendation context. So I would say part of it is, we're partially intentionally trying to avoid that that's part of it. But if you go back to our earlier work at the very beginning of the talk, I talked about this factorization model. And in essence, one of the things we're trying to do is basically, you know, find the features, sort of force them to be orthogonal to the sensitive feature, right? But even then, it's like, there's not like, if you think about like in the privacy literature where they've got differential privacy now, right? Which is sort of like, has nice sort of beautiful sort of guarantees about privacy leakage and kind of how you define that in sort of, if you propose a privacy preserving mechanism. Our challenge is, you know, we can propose a way to squeeze out a sensitive attribute, but I'm sure you're smart and would find a way to crack us and realize, no, actually you didn't do it. And we have no sort of theoretical guarantee where I could show you that I've done a good job of it. And so sort of to punt on your question, I think that's what, you know, I think we need more of that kind of formal mathematical sort of provable frameworks, because otherwise, you know, I'll propose something and you'll show how you can get around it. And then I'll show how I can get around what you did. And, you know, we'll go back and forth and we'll never be satisfied. But it is a big, big challenge. I think it's a really great question sort of for the community, for sure. And it's good to see you too, by the way.
Thank you. You always have more hair than I do.
Well, you got this great hair, so.
Hope to see you soon in conference in person. I echo your
everybody,
feeling there.
Thank you, Emilio. So with that, I think we're out of time, I'm afraid. But again, this was a great talk, and these were great questions. Well, you know, I'm not talking about my own. My own are never good.
It was a good question.
Yeah, thank you. So with that, I think we can end it, and Mara, you can